Hello, everybody. Thank you for joining us today. My name is Reynolds Pinto. I'm the Technical Sales Director for Applied Flow Technology. My email is reynaldopinto@aft.com. And I'll be hosting today's webinar where we'll be discussing a very critical problem, that is vibration. And it's critical because it creates a lot of operation interruption and plans due to failures. And that is the reason why the title of this webinar is Vibration a Headache? So we'll be discussing Energy Institute guidelines to avoid vibration problems from the design stage. If during the presentation you have any questions, type the questions in the chat room or the GoToMeeting, and at the end we'll have a session where we'll be discussing the questions, and if we don't have time to answer all of them, you'll receive an email with an answer to your questions. So today is a very ambitious webinar because it will try to cover in 1 hour a very extensive topic that is vibration. So keep in mind it's an introduction, and it will require on your side some reading and research to cover the details of the presentation. So today we'll have an introduction to the Energy Institute guidelines for the avoidance of vibration-induced fatigue failure in process piping, which provides a public domain methodology to help minimize the risk of vibration-induced fatigue for process piping. This is a guideline that has gained a lot of popularity in European and Asian countries, not so much in US. And we have seen it in Congress that we have attended both in Asia and Europe. Then we'll be discussing AFT new calculation spreadsheet that was created based on the Energy Institute guidelines. It's a new spreadsheet that will be available on our next AFT Fathom 12 release scheduled for October 2021. So some common causes of vibration is surge in momentum changes due to valve operation. As we know, when you close a valve partially or totally, it creates a pressure surge that travels down the pipe, and it creates problems it might create problems due to the forces that external forces that originates in the pipe, and it create and depending on the supports arrangement, it can be a hazardous condition or not. Another source of vibration that can create problems is cavitation. Cavitation is a dynamic process of formation of bubbles inside a liquid, which can suddenly form and collapse, and this can originate vibrations in your pipe that can also need to be addressed. Mechanical excitations, like high levels of vibration and failures, can occur when a pipe's network system has a mechanical natural frequency in resonance with the running speed of the machine, and resonance is one condition we want to avoid high vibrations in your problems in your pipe. So there are a variety of vibration sources which engineers can analyze in the system using AFT products. AFT Impulse PFA, which was released last year, can be used to analyze acoustical excitation and pulsation caused by reciprocating pumps. AFT Impulse is used to calculate pressure surge transient in liquid piping system caused by transient events. AFT Extreme PFA that was released this year is intended to address acoustical excitation and vibration caused by reciprocating compressors. AFT Extreme, which was also released this year, is used to simulate how your steam and gas system will respond to potentially harmful transient events. Beyond the vibration sources described in the previous slide, AFT new spreadsheet is intended to address the following vibration sources. Flow-induced vibration, FIV. For most cases, the dominant source of turbulence in straight pipe are major flow discontinuities. Typical examples are process equipment, partially closed valve, short radius, or mitter bends. These are reducers. So what we have here is we have the main pipe with a flow pattern that is altered by a discontinuity. In this case, we're talking about a T. This perturbs the flow that comes in the main pipe and creates a kinetic energy that has a potential to create vibration problems downstream the T. This flow-induced vibration can occur both in compressible and uncompressible flow. Another source of vibration that we addressed by the new spreadsheet is high frequency acoustic excitation, AIV. In a gas system, high levels of high frequency acoustic energy can be generated by a pressure reducing device such as a relief valve, control valve, or orifice plate. So what we have here is that we have a control valve reduces the pressure and creates turbulence downstream the valve that can create vibration problems downstream the valve. Acoustic fatigue is of particular concern as it tends to affect safety-related systems, such as when you relief valve opens or when you have a blowdown operation. Now, one particular thing about acoustic excitation is that the time of failure can be short, typically in few minutes or hours due to high frequency response, as well as giving rise to high tonal noise levels external to the pipe that can create hazardous condition for the operator, according to OSHA. So what happens is the vibration takes form of a local pipe flexure, resulting in potential high dynamic stresses levels at the circumferential discontinuities on the pipe wall, such as small bore connection, fabricated T, or welded pipe supports. So what you have here, we have an example in the graphic of a relief valve opening that creates a high acoustic vibration. And here we have a discontinuity that is a small bore connection. So it creates a shell vibration. And here, due to the high stress concentration factors in the connection, it can create failures in the small bore connection. Another source of vibration is pulsation. As we know, reciprocated and positive displacement pumps is a source of vibrations. So typical compressors, when they turn into the rotating stall condition, and also periodic flow-induced vibration due to dead leg branch thermal well, FIP. So what we have here is FIP. We have on the main street, we have the flow, and here's a connection, which in this case is a dead leg branch. So the flow creates a vortex that has a vibration frequency that if it coincides with the natural frequency of the connection, the side branch, it can create high displacement and create failure at the connection. So in conclusion, flow-induced vibration, periodic flow-induced excitation, high acoustic excitation will be addressed by IFT new spreadsheet that it was prepared based on the Energy Institute guidelines. Reciprocating positive displacement pumps and compressor is addressed already by AFD impulse PFA and AFD extreme PFA. One is for incompressible flow, one is for compressible flow. Surge and momentum changes due to transient event is addressed by AFD impulse and AFD extreme for compressible flow. Cavitation is addressed by AFD fathom and AFD impulse. So let's talk about the authors of the guidelines. Energy Institute. The Energy Institute is a not-for-profit professional membership body created with the purpose of bringing together expertise to tackle the urgent global challenges. It is located in UK. The Energy Institute was set up in 2003 as a result of a merger between the Institute of Petroleum and the Institute of Energy. So it provides a public domain methodology to help minimize the risk of vibration-induced fatigue of process piping. It is intended, and this is very important because it is intended for the use of engineers with no prerequisite knowledge of vibration. So if you don't have experience in vibration, you can use the guide to help you solve a problem. As we know, process piping have been traditionally designed on the basis of static design. So what we do is we do a stress analysis and lay down the supports to avoid, to comply with B31.3 or B31.1 or B31.4. But we pay little attention to vibration-induced fatigue. This is the main reason for this is because first, it's very difficult to predict the vibration, and second, most design codes do not address the vibration issue in a meaningful way. So they just tell you talk about occasional loads, but they don't really have a guidance on how to address any problem. So Energy Institute guideline uses an evaluation method for vibration failure possibility based on the likelihood of failure index. So depending on the index, it has certain measures to be taken depending on the value of the LOF obtained using the method. So guidelines, Energy Institute guidelines provide a stage approach. It's down by stages. First, it does a quality assessment in order to identify a potential excitation mechanism that may exist in your pipe. It can be used for new designs or existing plant network systems. It gives an overall quality assessment of risk qualification. So from the quality assessment, you will qualify your pipe as having high, medium, or low risk. Where an excitation qualification results in high or medium, you move to the second stage. The corresponding excitation mechanism should be subjected to a quantitative assessment, which is the second step of the guidelines. So here is the quality assessment table provided by the Energy Institute. It asks a question, and based on the response, it qualifies it as low, medium, high risk. And then it provides you guidance on how to solve it. Let's talk about number 4. The question here is, are there any positive displacement pumps in your compressor? If the answer is no, it's low risk. Your system is low risk. If the answer is screw gear pipe type of positive displacement machine, it's medium risk. If the answer is reciprocating type of positive displacement machine, it's a high risk. So then it provides you guidance in the section T2.4. In this webinar, we'll be talking about turbulence excitation, FIV. So we'll be using line 1. The question here is, will be here. What is the maximum value of the kinetic energy of your fluid, rho times V's velocity square of the process fluid with the system under consideration? So if it's below 5,000, it's a low risk. If it's between 5,000 and 20,000, it's medium risk. If it's higher than 20,000, it's a high risk. So then it provides guidance on how to solve any problems in section T2.2. So the second stage of the guidance is a quantity assessment, which is undertaken for each excitation mechanism identified in the quality assessment as high and medium risk. So in the previous step, if you detect that a system has a high and medium risk, you will do a quality assessment for it. So the resultant of this next step will be an LOF index, a score, likelihood of failure for each main line pipe, for each identify excitation mechanism. The primary difference between a quality and a quantitative assessment relates to the level of resolution in the analysis. The quality procedure requires less detailed information about the facility. Consequently, its ability to discriminate is much more limited. So your quality assessment is basically more general than your quantity assessment. So as I said, we'll be using flow-induced vibration as a source that we'll be using as an example on how to use the guidelines and how to use AFT new spreadsheet. In a future webinar, we'll be talking about AIV and how acoustic induced vibration, and we'll be showing an example on how to use the spreadsheet. But for this webinar, we'll be using FIV as an example. So the calculation of the LOF, the likelihood of failure for a flow-induced vibration, is rho times B squared multiplied by FBC divided by FB. So where rho is the actual density, V is the actual velocity. In this term here, rho times V squared is the kinetic energy of your fluid. FB is the flow-induced vibration factor, and we'll be seeing a procedure in the table T2-2 to calculate it. FBC is the fluid viscosity factor, which is 1 for liquids and multi-phase flow. So we'll be using this value as 1 because the example we'll be using is for liquid in a system. So the ground flow of the calculations of the LOF for flow-induced vibration is shown in this figure. So here, this section here is calculated by your AFT model. Rho times V, the kinetic energy of the fluid. In this section here, from then on, is calculated by the spreadsheet. So basically what it does is the spreadsheet will use the FBC, which in this case, the example we're going to follow is 1 equal to 1 because it's liquid. And then it determines your support arrangement. So there's a qualification of your support arrangement, whether it's flexible, rigid, or medium. And based on that, it calculates the FB. And finally, with that term here, we have all the terms to calculate the LOF. There's an advanced screening method option that is also calculated automatically by the AFT spreadsheet that is used for low frequency systems between 1 and 3, and it calculates a correction factor for the LOF that it applies to the LOF calculated by the traditional method. So the remaining factor to calculate the LOF for flow-induced vibration is FV. So first, we determine the type of support arrangement using the span length. So here's a table provided by the Energy Institute for the calculation of the support arrangement. And what it does, it qualifies your support arrangement, whether it's stiff, medium, or flexible. This determines the frequency range that your system is, natural frequency range for your system. For stiff, it would be 14 to 16 hertz. For medium stiff, it would be 7 hertz. For medium, would be 4 hertz. And for flexible, would be 1 hertz. So it calculates it based on the span and the external diameter. Basically, what it's doing is this table can be shown in this graph. Here is the span, and here's the outside diameter. And we can see in the graph that for high spans and low, for high spans, the system is qualified as flexible, and for low spans is qualified as stiff. So this is basically what the table is doing, qualifying your system, whether it's flexible, medium stiff, or stiff. Once your system is qualified as stiff, medium, it calculates alpha and beta factors to calculate your FB for using the external diameter. So your system is qualified as stiff, medium, and the spreadsheet, AFTF spreadsheet will calculate for you the FB factor. And with that, the LFF is calculated. So now we're going to discuss the spreadsheet procedure for the LOF. Before we do that, I'm going to bring the spreadsheet that you will have available in the new version of Fathom. So it has 4 tabs. First tab is for acoustic and induced vibration calculations. Second tab is for flow-induced pulsation calculations. Third tab is for flow-induced vibration for gases. And the first tab, which we'll be using in this webinar as an example, is the flow-induced vibration calculation for liquid. All the instructions and everything the spreadsheet will come with an instruction manual that is basically a description for each type of vibration calculation method, and we'll be following the procedure that we'll be describing is already given to you in this instruction manual for the use of the spreadsheet. So let's start. Procedure. How to use your spreadsheet in AFT. First, you run the model and you get results. Second, you determine the pipe to be analyzed for flow-induced turbulence. Then, from the workspace, you click the Excel Export Manager button on the toolbar, then you click Open. So here up, there's an icon that's that will open the Excel Export Manager, and you click Open to start creating your export spreadsheet. The blank Excel Export Manager will appear. With the Export Manager open, you click New Add Row, then input the following rows using the image below in the table as a guide base for the fluid type. I'll bring the spreadsheet again. And the spreadsheet tells you in colors the user input, the export input, and the results input. So some information you will have to input, some will need to be exported. We can see in the table in blue that we need to export from the model the internal diameter, the density, and the velocity. That is why in the spreadsheet for flow-induced vibration, you see 3 lines for the same pipe. Diameter hydraulic, density of the fluid, and the velocity. So we will create, when we examine or we calculate the LOF for a pipe, 3 parameters that are needed by the spreadsheet for the same line. So the pipe number shall be the same for all the rows, because we need to export the information for the same pipe that the spreadsheet requires, that the hydraulic diameter, the density of the fluid, and the velocity. The export parameters will be the ones indicated in the spreadsheet in blue. As I said, in blue tells you that you need to export it from your model: diameter, density, and velocity. Diameter, density, and velocity. And another important thing is that the units will be the same as the tables. Diameter is exported in millimeters. Density is exported in kilograms divided by cubic meters. And velocity is exported in meters per second, because the Energy Institute guidelines use those units to establish the correlation for the guidelines. The next step is at the bottom of the Excel export location, you select currently open workbook. I like to open the spreadsheet before to make sure that I export to the correct spreadsheet. And you have to make sure it's navigating to the flow-induced vibration calculation file, or if you gave it another name, make sure it navigates towards that. Oh, one thing I forgot. Once all the inputs are confirmed to match the windows, you click Export button to the left, Export. AFD will export the parameters in the spreadsheet, which has a pre-built calculations. With the value AFD fathom enter, users specify the remaining values of the input. So here, the user has to input the span, the thickness, and if you measure the vibration in the field, then you input the vibration frequency. If the natural frequency is not known and you can't measure in the field, the typical fundamental natural frequency will be calculated by the spreadsheet using the guideline procedures. The LOF is calculated as shown in cell C19 of the input section. And the use of the energy, you should use the Energy Institute guidelines to determine the appropriate actions based on the LOF value. So the LOF Energy Institute guidelines provide guidelines for the actions you need to take in case there's a problem indicated by the LOF. Here's the table for the correction actions. If your LOF is above 1.0, then it provides guidelines on how to address the problem. If it's between 1 and 0.5 and 1, then it provides you guidelines for the same. and so on for the other values. Also, it has a section that provides in detailing, as the one indicated here, the description of the solutions that you will that will help you solve the problem. So the general in section T10.1.1, general corrective actions affecting pipe work response. In the case of FIB, which we'll be using as an example here, it is described in section T10.2, and the solution it provides is separated for the mainline excitation and the mainline response. For the mainline excitation, it suggests either reduction of the fluid velocity, flow smoothing, change valve type, and change valve trim. All of this is described in details in each one of the sections. For the mainline response solution, it provides changing the supports of your pipe, using viscous dampers, shock arrestor or snubbers, composite pipe work wraps, or change in the section wall thickness. So now, let's talk about an example of IFT. So what we have here is, based on in the field, you're observing vibrations in P4 and P8 caused by the control valve G4 and G7. And you want to see whether or not this vibration problem is too high. And if it is, if it requires an intermediate support, this is a possible solution. And so we'll be calculating the LOF for P4 and P8 that we are observing high vibrations. The field support distance for these pipes is 6 meters, and there are 3 inches, schedule 40, and the thickness is 5.4.6. So I'll be bringing AFT Fathom. So here's the section, the model that we created. We want to study, as I said, the vibration problems that we are observing in the field in P4 and P8. I created in a scenario for the checking the FIB for P8, for pipe 8. So the first step is to run your model. Once we get the result, we come here to this icon here, and we click on it, we select it, and we open it. So now we've created 3 lines to export the information required by the spreadsheet from a new spreadsheet from AFT. We're checking, as we said in the spreadsheet, the spreadsheet requires you to export the diameter, the density, and the velocity. So here, we see that we're exporting the diameter in millimeters because it has to have the same units. the density of the fluid and the velocity in the same units. And here, since we're going to do a flow-induced vibration calculation, we direct it to the Excel sheet, FIB calc for liquids, which is the name for the tab for this type of calculation, FIB calcs liquid. It has to have the same name. So now the next step is to select, if you don't want to open it and you have to save it, so you would say previously saved and save work with. As I said, I prefer to open it to make sure it exports and I can see it exporting. So in this example, we will select currently open workbook, and we make sure it's directed to the flow-induced vibration calculations spreadsheet that is provided by FT. You can change the name of the spreadsheet, but be sure it has the new name you provided to the spreadsheet. Once we do that, then we hit export now. So it tells us it exported without any problems. We bring the spreadsheet and it creates a new tab telling us what it exported. So now we will to the spreadsheet, and we can see that it exported the density, the diameter, the density, and the velocity. So now we have to input the span. As we said, it's 6 meters. And the thickness is 5.48. With that, it will calculate the likelihood of failure index, the LOF, which is 0.4, according to the Engineering Institute guidelines, is 0.475. So what did the spreadsheet do? And it shows it to you. In step one, it calculated the kinetic energy of your fluid. Then it calculated the fluid viscosity factor, which is 1 because it's liquid. Then it qualified the support based on the distribution of support. Here in green, it highlights the type of support you have. You see, we have false, so here it will highlight the type of support. For 6 meters, it would be medium stiff. It would be medium. It would have a frequency of 4 hertz. And then it calculates the FB factor based on the type of support distribution that you have. So it calculates the beta and the alpha factor, and finally it calculates an FB of 10,845 as a value. So finally it calculates the LOF for you, that it's 0.475. With this value, we would go to the table, and say, okay, our value is between it's between 0.475. So it's not a major problem. So really the vibration that you observe in the field will not cause problem according to the energy guidelines. So no action needs to be taken. So let's do an example for pipe 7. We'll create a scenario to check the flow-induced vibration for pipe 7. So I will copy this. So as the first step, we run the model. We say, okay. Calculation completed. Say output. Now we come here and we open the spreadsheet. We select pipe 7 because it's the one that we're going to change. We're going to examine here. We export the diameter, the density of the fluid, the velocity, the same units, same cells in the spreadsheet. So we go down. We make sure the currently open workbook is selected to the flow-induced vibration calculations, and we hit export now. It tells us it was exported without problems. So now we open the spreadsheet. The same, it has the same span, the same thickness, and it calculated 0.75, which tells us there's no problem again with this line. Look what happens if I increase the span. Let's say instead of 6 meters, it's 8 meters. So now the LOF, likelihood of failure, is 1.6. And according to the table, let's see the guidelines table. For LOF, the main line shall be redesigned, resupported, or a detailed analysis of the main line shall be conducted and vibration monitoring. So whenever the vibration, the LOF is higher than basically 0.5, it tells you for flow-induced vibration, this can create a problem. So you need to take actions on that. So now we enter to the section of questions. Is there any questions that you have? I'll open the chat room. Okay, where can we get the spreadsheet? As I said, it will be available for you right now. It's ready. It's being revised, and the spreadsheet will be available for you in October with the release of a new version of Fathom 12. So yes, it will be available for you at no extra cost with the maintaining and support of the AFT software. There's another question here is, Fathom doesn't address warning that will flag potential vibration issues with the model, right? Correct. Fathom is designed, well, if a vibration problem that caused by cavitation, it will give you a warning that cavitation is happening. But for flow-induced vibration and acoustic-induced vibration, and this type of source of vibration, the Fathom does not address it directly. So if you observe vibration in the fields also, or want to check it before in the design stage, you would have to use Energy Institute guidelines, and that is why the spreadsheet was created to help you use these guidelines to prevent vibration problems. Let me see if there's another question. What is the difference between this method and AFT PFA analysis? Well, PFA is more precise because it's an acoustic analysis, and it allows you to examine the acoustical natural frequency vibrations, and it tells you, but still the guidelines can provide you solutions. So you can use them both, PFA and the guidelines to address any problems you foresee. So the guidelines will basically provide you solutions, and PFA will provide you the exact acoustical frequencies in your pipeline. So you can either implement acoustical solution or mechanical acoustical solutions. Let me see if there's another question. Let's see. Do we need to input the pipe material and the non-metal? Well, the guidelines are made for Energy Institute guidelines are designed for steel pipe. If you have a different material, I don't know if the guidelines would apply. Is there a similar spreadsheet for all? Yes. The acoustic induced vibration is for gases, so the spreadsheet will also be available for aero and for impulse. See if there's any more questions. Okay, so there's no more questions. You can send me if you have more questions or about this new spreadsheet. You can send it to me. Yes, it's very the Energy Institute guidelines are very useful, and I hope you can take a look at it. And we hope that the spreadsheet will help you implement the guidelines easily. So as I said, we're going to do a similar webinar, but now with a acoustic induced vibration for gases. So stay tuned for our next webinar on Energy Institute guidelines for acoustic induced vibration, source of vibration. Thank you for joining us today. As I said, if you have any questions, just let me know. So what is next? You will receive a follow-up email with the link to the recorded webinar. You can join us at the upcoming webinars at AFT.com Learning Center webinars, upcoming webinars. And you can request an evaluation at salesaft.com. And if you require pricing information, in USA, it's posted in a web page. And internationally, you can contact your local channel partner. Thank you again for joining us. Hope this was interesting for you, and hope to see you in our future webinars. Thank you again.